Hi, I am Amir and welcome to the first episode of Knockout Math. In this program, we are going to talk about mathematical functions, what they are and how they are used. Functions are one of the most important topics in math, and they show up in all kinds of fields like astronomy, 3D graphics, civil engineering, sound waves, stock market analysis, robotics, and more. Let's start by defining what a function is. Imagine a factory that takes in raw materials, does some processing, and produces a product. For example, think about a factory that takes milk and turns it into ice cream, or another factory that takes paper and turns it into books. Functions work the same way in math, but instead of working with physical materials, they work with numbers. They take a number as input, process it, and give you another number as output. For instance, function q takes 3 and turns it into 6. Basically, functions take an input, like x, and turn it into an output, like y, through some process. This is the general idea of a function. Now, let's look at some example. In the function f(x) equal x divided by 2, if x is 2, you just replace x with 2. So f(2) is 2 divided by 2, which equals 1. Or take the function f(x) equal x squared. If x is negative 3, then f negative 3 is negative 3 squared, which equals 9. Another example is g equal to the square root of a plus 1. If a is 15, then g15 is the square root of 15 plus 1, which equals the square root of 16 or 4. One more. In the function ga equals the absolute value of sin a minus 1. If a is 0, then g0 is absolute value of sin 0 minus 1. Since sin 0 is 0, this becomes the absolute value of 0 minus 1, which equals the absolute value of negative 1 or 1. Now there is something special about functions. They can't give more than one output for the same input. In other words, for every input, you either get no output or just one output, never more than one. For example, if a function takes milk as input, it can't give you both ice cream and shoes as output. That wouldn't be a function. Similarly, for example, if a function takes 2 as input, it can give you both 4 and negative 1 as outputs. But if a function takes 2 as input and gives you 4, and then takes 3 as input and gives you negative 1, that is totally fine. That is a valid function. Here is another example. If a function takes 0 as input and gives you 1 and also takes 1 as input and gives you 1, that is still a function. Why? Because we say the single input cannot have more than one output, but it's okay for different inputs to have the same output. So to sum it up, a function is something that for every input gives you at most one output. For example, in f(x) equal the absolute value of x, if x is negative 2, f negative 2 is the absolute value of negative 2, which equals 2. Here is another example. In absolute value of f(x) equal x, if x is 3, then absolute value of f3 is 3. But what if there is a function where f3 could be 3 or negative 3? That wouldn't be a valid function because a single input would have two outputs. To check if a graph represents a function, you can draw a vertical line. If the line touches the graph in more than one place, it is not a function. But if it touches the graph at only one point, then it is a function. Now let's talk about the domain of function. Remember the milk and ice cream example. The factory cannot take shoes as input and produce ice cream. So all the inputs that the factory or function can work with are called the domain. For instance, in the function ga equals the square root of a plus 1, if a is negative 2, then g negative 2 is the square root of negative 2 plus 1, which equals the square root of negative 1. That is undefined. So the function can't accept inputs less than negative 1. The domain of g is all numbers greater than or equals to negative 1. So the domain of a function is basically all the inputs it can handle. Next up is the range of a function. What is the range? Well, it is all the possible outputs of a function. For example, if function f takes milk as input and gives ice cream as output, you can accept it to give you shoes. So the range is just ice cream. In another example, if ga equals the square root of a plus 1, the domain is all numbers greater than or equal to negative 1, the outputs will always be greater than or equal to 0. For instance, if the input is negative 1, the output is 0. If the input is 0, the output is 1. This function will never give you a negative output. So the range of function g is all numbers greater than or equal to 0. The next topic is one-to-one functions. In the definition of a function, we state that one input cannot have more than one output. But it is okay for different inputs to have the same output. A one-to-one function, though, is a little stricter. In a one-to-one function, every input has a unique output. No two inputs can share the same output. For example, take the function fx equal to x plus 1. This is a one-to-one function because no two different inputs give the same output. To prove this, let's assume two inputs, like a and b, produce the same output. So fa equal fb, that means 2a plus 1 equal 2b plus 1. If we simplify this, we get 2a equal 2b and finally e equal b. Since a must equal b, it proves the function is one-to-one. Now let's look at the function fx equal x squared. This is not a one-to-one function. Why? Let's assume two inputs like a and b give the same output. So fa equal fab. That means a squared equal b squared. Simplifying this, we get a equal positive or negative b. For example, if the output is 4, the inputs could be 2 or negative 2, since two different inputs give the same output. This isn't a one-to-one function. Here is a challenge for you. Can you prove this function is one-to-one or not? If it is, explain why. To check if a graph represents a one-to-one function, draw a horizontal line. If the line touches the graph at more than one point, it is not a one-to-one function. But if it only touches the graph at one point, then it is a one-to-one function. Now let's talk about the inverse of a function. A function has an inverse if and only if it is one-to-one. The inverse of a function is written as f inverse x. For example, if fx equal to x plus 1, the inverse of this function is f inverse x equal x minus 1 divided by 2. Why does this work? First, we check the function is one-to-one, which we already prove it is. Then to find the inverse, we solve for x in terms of fx, rearrange the equation fx equal to x plus 1 becomes x equal fx minus 1 divided by 2. Finally, substitute back and you get f inverse x equal x minus 1 divided by 2. Next, let's look at the different types of functions. The season is just an introduction, but in future seasons, we will dive deeper into their properties and relationships. Linear function. This is fx equal x. A linear function gives you the same output as the input. For example, if you input 10, you get 10. If you input 0, you get 0. If you input negative 10, you get negative 10. To graph it, just pick a few inputs, calculate their outputs, and plot them. Connect the points, and you get a straight line. Quadratic function. This is f(x) equal x squared. A quadratic function squares the input. For example, if you input 2, you get 4. If you input 0, you get 0. If you input negative 2, you also get 4. When you plot it, the graph looks like a U-shaped curve. Absolute value function. This is f(x) equal the absolute value of x. It takes the input and makes it positive. For example, inputting 20 gives 20. Inputting 0 gives 0. And inputting negative 20 gives 20. The graph looks like a V shape. A square root function. This is f(x) equal the square root of x. It only works for non-negative inputs because you can't take the square root of negative number. For example, inputting 0 gives 0, and inputting 4 gives 2. The graph starts at the origin and curves upward. Exponential function. This is f(x) equal to the power of x. For example, inputting 0 gives 1, inputting 2 gives 4, and inputting negative 1 gives 1/2. The graph grows really fast as x increases. A step function. This is f(x) equal the floor of x. It gives you the largest integer less than or equal to the input. For example, inputting 1.5 gives 1, inputting 0.8 gives 0, inputting negative 0.7 gives negative 1, and inputting negative 1.2 gives negative 2. The graph looks like a series of steps. Logarithmic function. This is f(x) equal the logarithm of x to base 10. For example, inputting 1 gives 0, inputting 10 gives 1. The graph grows slowly as x increases. Trigonometric function like sin function. This is sin x. For example, inputting 0 gives 0, inputting 90 degrees gives 1, inputting 180 degrees gives 0, inputting 270 degrees gives negative 1, and inputting 360 degrees gives 0. The graph is wave-like curve. Inverse trigonometric function. This is sin inverse x or arc sin x. For example, inputting 0 gives 0, inputting 1 gives 90 degrees, and inputting negative 1 gives negative 90 degrees. The graph is restricted to the range of the sin function. Hyperbolic sin function. This is sin h x. For example, inputting 2 gives about 3.6, inputting 0 gives 0, and inputting negative 2 gives about negative 3.6. The graph looks similar to an exponential curve. Inverse hyperbolic sin function. This is sin h inverse x. For example, inputting 5 gives about 2.31. Inputting 0 gives 0, and inputting negative 5 gives about negative 2.31. The graph is the inverse of the hyperbolic sin function. The next topic is function composition. This is about combining two functions into one. Basically, you take the output of one function and use it as the input for another. Here is how it works. Let's say you input x into function g. The result gx become the input for function f. This combined process is called the composition of the two functions and is written as f of jx or f of jx. It is important to note that f of jx and g of fx are not the same. In f of jx, function g processes x first, and then its result is passed to function f. In g of x, function f processes x first, and then its result is passed to function g. Let's look at an example. Suppose fx equal 2x plus 1 and gx equal x squared. To compute f of gx, you replace x in f with gx. So f of gx become 2 times gx plus 1. Since gx is x squared, substitute it in and you get 2x squared plus 1. Now for g of x, first compute fx, which is 2x plus 1. Then use it as the input for function g. So g of fx becomes g of x, which equals fx squared. Substituting fx equal 2x plus 1, you get 2x plus 1 squared. Now let's talk about the domain of function composition. We know the domain of a function is all the inputs it can accept. For a composition like f of gx, the inputs must work for both g and f. This means that x has to be valid for g, and the result of gx must also be valid for f. Here is an example. Suppose fx equals the square root of x and gx equals 1 divided by x. The domain of g is all real number except 0, because dividing by 0 is undefined. The domain of f is all non-negative numbers, because you can take the square root of negative number. For the composition f of jx must produce outputs valid for f. Since gx is 1 divided by x, it has to be greater than or equal to 0. So the domain of f of jx is all positive number greater than 0. In this season, we have covered the basic of functions, their properties, and some common types. We have also discussed how to check if something is a function, what one-to-one functions are, how to find the inverse of function, and what function composition is. In future season, we will go deeper into these topics, exploring more example, calculations, and relationships. I hope you find this season helpful. See you in the next one.